Hello, this is a follow-up presentation to a former presentation that has already been recorded on the general linear model. So in presentation one, I showed parts of the general linear model on a slide that looked like this. And as I recall, that presentation basically got this far through t-tests and ANOVA. So where are we going to go from here is to areas that were not covered in that presentation, plus a few more. So the first thing we're going to look at is the case, and we're just going to look at that for a little bit, of we're continuing along this line where we start with deciding what the nature of the X and Y variables are. But we're going to go down this track to where you have multiple continuous Y variables. In other words, you're trying to predict not just, for instance, blood pressure, but cholesterol level and folic acid level. And what you have as a predictor is one or more categorical variables. For instance, pregnant versus non-pregnant women, or men at ages 40, 50, and 60. So those are categorical variables. The second one is ordinal. But we're going to use those to predict three dependent measures of a medical status. And the higher level that is predicted here is what's called a repeated measures ANOVA. These all fall into the general area of ANOVA. They're not really shown here as ANOVA type variables, but this is considered a repeated measures ANOVA. And it allows, for instance, not only three dependent variables that are measured at the same time, but three dependent variables that are all the same that are measured over time. So it can be a time varying dependent measure, which has many uses. The other one is MANOVA, which is multiple ANOVA and is more frequently associated with the first three dependent measures that I illustrated, where the three dependents are not time varying. Regardless, repeated measures and MANOVA are quite similar designs, but the main characteristic of them is that you are measuring multiple continuous dependent variables at the same time as predicted by categorical variables. And you can also, if you choose, add in covariates as recovered previously with ANCOVA. So you can have repeated measures ANCOVA, and you can have what's called MANCOVA in these designs. So I don't want to spend too much time on the ANOVA related designs. What I want to get into is the very much broader kind of design that is answered in multiple regression. And it is what we consider more frequently as part of the general linear model, but they are all part of the general linear model in that they are all modeled using ordinary least squares regression, or that can also be looked at. I find it easier to think about the t-test and the ANOVA group of designs if you think of it as having to do with deviations and the normal distribution. So here are the designs that derive the simplest kinds of analyses that derive along the correlational version or the regression version of the general linear model. And I should have highlighted this, but in each of the cases that are colored here, you have a single dependent variable, which is continuous. So something like scores on the Beck depression inventory. And you have a continuous predictor. So something like anxiety. And what you're looking at is the relationship between anxiety and depression. So if you only have these two variables and they're both continuous, but you only have the single, a total of two variables, and both x and y are continuous. So you have one x predicting one y. You basically are going to do that with the bivariate correlation. There are lots of different types of bivariate correlations. Actually, there are bivariate correlations that relate to when you have x's in different forms or even y's in different forms, but we're not really going to spend any time on those in this presentation. So what we're also going to look at is the possibility that you have this continuous x, but you have multiple. And those can be, as I said, with bivariate correlations, actually categorical x's as well. It really doesn't matter. You're going to associate categorical x's more with the ANOVA or t-test design, controlled versus treatment, pregnant versus non-pregnant. But if you have continuous variables and categorical variables, it is often the easier, provides easier interpretation if you use those categorical variables in a simple multiple regression design. And remember, these are both, whether you're in the ANOVA world or you're in the regression world, they are both parts of the general linear model. The reason I distinguish them at all is because they are traditionally taught in different clusters, and it's easier to think of them in different clusters. So I would say that if you maybe just have one or two continuous variables and they're not variables of research interest, they are what we call covariates, and the variables of interest for the research are the categorical ones, then you should do an ANCOVA. But if you are interested in terms of your hypotheses about in both the continuous and the categorical variables, or perhaps you're not even particularly interested in the categorical variables, then you would generally look at that through the lens of multiple regression. And multiple regression basically is a method for looking at multiple continuous and categorical variables as predictors of a single continuous dependent variable. And in this, and these are more, it's particularly mediation and moderation are more design characteristics, but they are things that you can look at with different kinds of multiple regression. So if you want to look at mediators, you would usually do something called a path analysis, which is a more sophisticated approach using multiple regression techniques that looks at whether a single X predicts Y through the path of Q. So before a intervention affects achievement, is it necessary for that intervention to be mediated by an impact on motivation. So the intervention affects achievement through the mediating value variable of motivation. So path analysis, which is related to a broader kind of analysis, which I will illustrate later, is a sophistication of multiple regression for a particular kind of hypotheses. So some of these relate more to different kinds of hypotheses than actual techniques. And I would consider mediation a kind of multiple regression technique. And that's going to happen more often as we go through these slides where there are overlaps. And that again is because we're looking at the general linear model. So multiple regression can also be used to look at moderation. And those in the ANOVA world are considered interactions. So if gender moderates the effect of an interaction on achievement, then it's an intervening variable. The interaction predicts achievement, X predicts Y, but its relationship to achievement is contingent on the effect on gender. It affects men differently than it affects women. So, I look at the Alcoholics Anonymous program. So that's your X variable. And there are some theories that because traditionally it was created by men, predominantly for men, and it has kind of a traditional pre-feminist approach to alcohol addiction recovery, that it is more effective with male alcoholics than it is with female alcoholics. So the effect of the Alcoholics Anonymous program is contingent on sex, and that's considered a moderator. And it's the same as what we talk about in factorial ANOVA as an interaction. And that can be modeled just as it can be in a ANOVA design through multiple regression. The nice thing about multiple regression is that you can look at interactions between continuous variables, and you can look at interactions between a combination of continuous variables and categorical variables. And a third sophistication of multiple regression is something that you've probably seen quite a bit in the literature, which is called hierarchical linear modeling, which is when you have a nested structure. So a nested structure means that you have the intervention the effect of the intervention is not only part of the direct effect of an intervention on students, and it doesn't actually even have to be. There doesn't have to be an intervention present, but it's when you're looking at the effect, say, on students of not only their own characteristics, but the characteristics of the teachers that teach in their classrooms, and perhaps the schools where those teachers are employed. So what we say is that the students in the classrooms are nested within their teachers, and their teachers are nested within their schools. And it's an important design because when you look at the effect of, let's say, a reading program on individual student achievement in reading, that achievement may be affected by a host of factors that we say to be at the student level. And those would be student prior achievement. They might be the socioeconomic conditions of their home. They might be the number of books in their home. But they're also going to be affected by things at their classroom level, such as the teacher training, the teacher implementation of the reading program. So we've looked at implementation. That might very well be a second level factor that you'd see in hierarchical linear modeling. It's not the implementation at the individual student level, it's implementation for a whole little cluster of students nested within that teacher. And the teachers in the school, perhaps their implementation is going to be affected considerably by characteristics of their school. The experience of the principals, the school zip code, all kinds of different factors. And so that's considered a nested structure. You have explanatory variables, not just at the level that is expected to have kind of the final change in reading achievement, but at systematic structural variables that also vary for their own reasons, but relate to the student outcomes. So that's analyzed with hierarchical linear modeling using a nesting structure. I'm going to point out, I don't think it shows up on other slides, but the hierarchical linear modeling is associated with multiple regression. There are other ways outside the general linear model of looking at nested structures. And that becomes true more often as we go through the remainder of these slides. So this is just to let you know that there are not only, and this came into, for instance, mediating variables, there are design characteristics that become more and more associated with the types of modeling that you're going to use. And one design characteristic is whether you are going to statistically match the people in your sample with comparable students. And the one very primitive way of doing this in the ANOVA world is to control for covariates that may cause differences prior to or post assignment to groups. So those fall into the ANCOVA world. And that would be just basically if you usually just had a few background characteristics like prior achievement or pre-test that you considered likely to have an effect prior to treatment on student outcomes, but what you were interested in was the effect of the intervention. So you were just kind of sucking up, as it is sometimes said. You're controlling for background variance, but what you're primarily interested in is you have some kind of assignment to group. You are actually comparing two groups. Another approach to statistical matching is called propensity score analysis. And that is where you have your sample, and then you have another large pool of people who are theoretically comparable to your sample, but are not part of a group that you have actually had any control over or really selection in the process of. And what you do is you use statistics to find people within that sample who have a similar propensity to have become part of your sample as the people actually in your sample. And you do that by statistically matching using background characteristics, basically as many characteristics as you possibly can, to statistically create values for people who don't exist, but who are kind of they have scores, but their scores have been adjusted to make them as similar as possible to the people in your sample. And you get the best match if you don't have to adjust their scores considerably, and if their scores end up very close to the scores in your sample. And that's the design that allows you to basically compare groups using some form of multiple regression usually, or some application under the general linear model. But it is a design characteristic, not actually, it's a design, it's a statistical method that comes before the primary analysis. It's a pre-analysis or pre-technique to actually construct the sample. And there are other types of things like that, like missing data imputation, which is when prior to analysis using multiple regression or whatever you're going to do, you first correct your sample for scores that are missing on various predictors. And you impute those scores, you create those scores based on known information about the people who should have had those scores. And there are multiple ways to do that. So now we have something that is quite different. We have the case where, according to the nature of X and Y up at the top, we kind of change things so that Y, rather than being continuous, is categorical variable. And there's just one categorical variable that's being predicted. And if you also are relating that to a single independent variable, but really with this method, there is no independent and dependent, they're just two categorical variables. You use the chi-square analysis. And you've probably used chi-square analysis in a first semester class. So I'm not going to really go into any detail, except that it's primarily used for comparing the relationship, for understanding the relationship, at least for our purposes, understanding the relationship between one categorical variable and another, or sometimes ordinal variables. And this whole area has a slightly gray background, and that's because it is not necessarily part of the general linear model. Chi-square is not. Chi-square is a non-parametric test, which means that it doesn't use ordinary least squares regression, and it does not depend on the assumptions of the normal distribution. And while logistic regression, as you noted, has the word regression in its title, can be performed and often is performed using the general linear model. There are other ways of modeling the case where you have a categorical dependent variable and are predicting it. For instance, this is if you're predicting school dropout, yes or no, this would be what the technique you would need to use. So I did a propensity score analysis design where we were predicting being on track for college at the end of 10th grade, yes or no, which schools have a way of recording. We were predicting possibly high school graduation, and we were predicting a binary variable about whether students had met the conditions for entering CUNY without need for remediation, yes or no. So those were logistic regression analyses. We also used propensity score matching, and I believe we used missing data imputation on that. I can't really remember, but the method we used once we had crafted the sample for the analysis was logistic regression, because we were predicting the binary variable, for instance, entering CUNY without need for remediation. And just like any other regression, this can be used with hierarchical linear modeling. It can be used to look at moderating variables or mediating variables. And it can be used with all of those design characteristics that I named before. For instance, propensity score matching and multiple data imputation, missing data imputation. Those are almost more like data cleaning analyses or setting up a sample. Missing data imputation might fall under data cleaning, as might other things like variable transformation. There are a lot of techniques that can be done as part of setting up the sample for analysis. And sometimes we call that an analytic sample. The sample that's actually going to be analyzed using logistic regression or multiple regression or whatever. But since we've run into propensity score analysis so frequently, I wanted to add it in here. So let's see what else we have. We have the new design here where you have multiple Ys and they're continuous. And we're not going to be looking at the ANOVA world because we're going to have the situation, or MANOVA or repeated measures, because we're going to have the situation where the X's, the variables of interest, are continuous. So you've got many X's predicting many Y's. And usually you'll see this in some kind of measurement or big relationship study. And I've also put a gray background in, and those are variations on factor analysis. And I put a gray background in these because they can be analyzed using methods besides the general linear model. And I probably shouldn't have put that gray background under exploratory factor analysis, because it is very typically analyzed using ordinary least squares regression or the general linear model, but not necessarily confirmatory factor analysis that does hypothesis testing or latent variable analysis. And just to distinguish, so there are arrows both coming from the multiple regression world to these three, and from this kind of outside world that has the gray background, which is beyond the scope of this class, but there are very many alternatives to the kinds of modeling we do in ordinary least squares and the general linear model. Basically, they're models that do not necessarily assume the normal distribution and do not necessarily assume linear relationships. But for the purpose of looking at these in terms of the general linear model, they use multiple regression techniques, and a factor analysis can be done in 3 ways, or can be used in 3 ways. It can be used to look at the measurement structure in an exploratory way of a proposed scale, to look at the dimensionality of that scale. And in that case, you'll have item scores predicting other items. scores. So you say have a 20-item instrument that you have developed, and you assert that 10 of the items are relating to one dimension of your construct of interest. So you're looking at motivation, and you consider that motivation at the individual level is a combination of expectancy to be able to perform a task well, and how important you think the task is, value. So this is the expectancy value theory. It's rather old and fairly well established at the individual psychological level. It's doesn't bring in a lot of social contexts, and so it is limited in its use. But let's say that you have an instrument of 20 items, and your measurement hypothesis, which you don't really test in an exploratory, but what you investigate in the exploratory analysis, is whether 10 items that you assert are related to expectancy, and the 10 items that you assert relate to value, actually statistically cluster. The responses statistically cluster in those two patterns. So that's called an exploratory analysis because it doesn't do any hypothesis testing. So let's say that you first explored that and you found that indeed the 10 items that you found, very luckily, first run, that the 10 items that you claimed related to, or you hoped would relate to expectancy, all clustered around one thing, and the 10 items that you hoped would relate to value all clustered around something else. You then could test that hypothesis, and you would use a new data set, and you could perform a statistical test, or actually a variety of statistical tests, to discern whether that hypothesis that the item responses did cluster in those two different dimensions. And cluster isn't a very exact term. You're more likely to say that they load on the factors. There's a whole different area called cluster analysis. I'm using these terms more for the purpose of intelligibility and communication than necessarily their technical exactness. So you'll often see that items load on a factor. So 10 items load on the factor that you are calling expectancy, and 10 items load on the factor that you're calling value. And that's, if you run that data and set up the structure of the data so that you are actually able to test the hypotheses that not only do these items cluster in those two dimensions, but that they explain a proportion of the variance that is higher than if there were some other structure. That's called confirmatory factor analysis. And structural equations modeling is basically when you have multiple models that are predicting these dimensions, like expectancy and value, but they're not just predicting items, they're predicting scores on those other things that are themselves composed of multiple items. So they might be predicting expectancy, and value might be predicting persistence on a task. And the persistence itself would be constructed, would be a latent variable constructed by its own set of items. So you get what's called a structural equation, in that your items for expectancy and your items for value all load on these things you're calling expectancy and value. And the expectancy and value they're called latent variables now because they're constructed of actual items, predict persistence. And persistence, like expectancy and value, is a latent variable that has been, as it were, formed out of individual items or individual subvariables. So that's the world of factor analysis and structural equations modeling. And as I said, particularly confirmatory analysis and structural equations modeling can be and often are solved through types of analyses other than the general linear model, but also the general linear model in a complex multiple regression approach can be used to construct all of those tests. And that's it for this presentation, and I hope that it was useful.